All right, guys, it's time for fun with math. And today we're going to talk about something called trigonometric integrals. But first, I want to review some trig identities with you because we'll need these trig identities to solve these types of integrals. So let's start up here, which is the simple reciprocal identities. So what are these? The idea behind these is it's possible to express secant of theta, cosecant of theta, and cotan of theta in terms of the big three. So it's always opposite the letter. So if it's S, it's C. So it's 1 over cosine of theta. And then this one is 1 over sine of theta. And finally, cotan of theta will equal to 1 over tan of theta. And so this will allow us to convert any secants, cosecants, and cotans into sines, cosines, or tans, basically. And then the quotient identities, they kind of finish this off. So for the quotient identities, what we have is we can actually express tan of theta and cotan of theta in terms of sines and cosines. And so this is going to be equal to the tan of theta is the sine of theta over cosine of theta. And the cotan of theta is the cosine of theta over the sine of theta. So it's just a flip, the reciprocal. And so you need to make sure that you know these. And if you don't know them, just make little note cards, put the secant of theta on front and 1 over cosine of theta on the back. Because the idea is when we do trigonometric integrals, they're just integrals involving trigonometric expressions. So you might have something like secant theta divided by cotan theta, d theta. And in order to integrate that, we're going to have to convert these often to sines and cosines. So you have to use this identity here and this identity here. And when you do that, this problem will simplify and we'll have a chance to actually integrate it, which we'll do in a little bit here. But before we do those, we have a few more identities we need to make sure that we're familiar with. So the Pythagorean identities. So these are a big one. These come right from the unit circle. And so the first Pythagorean identity is cosine squared theta plus sine squared theta is equal to 1. And so we all need to know that identity. And then there's two other identities that go with this one. And I think I showed you guys this in class, but the idea is just divide everything by a cosine squared theta and something nice will happen. So over here, when you divide by cosine squared theta, you just get a 1. Plus, right here, when you divide by cosine squared theta, you get a tan squared theta. Equal to then, and when you divide 1 by cosine squared theta, you get a secant squared theta. And so there's a second Pythagorean identity. And the third Pythagorean identity is given not dividing by cosine squared theta, but dividing by sine squared theta. So if you divide right here by sine squared theta, you're going to get a cotan squared theta. So we get cotan squared theta. And then we have a plus right here, and we divide sine squared theta by sine squared theta, you're going to get a 1. And then it's equal to, then 1 over sine squared theta is a cosecant squared theta. And so there's the third Pythagorean identity. But wait, there's some more. And so we have these double angle formulas, which actually don't pop up that much, but it's nice to know them from time to time. So the double angle formulas answer these two questions. What is sine of 2 times an angle? So sine of 2 theta versus what is cosine of 2 theta? And so sine of 2 theta is equal to just 2 sine theta, cosine theta. That one I just straight up memorize. And same with cosine of 2 theta, straight up memorize this one. So this one's like this Pythagorean identity here, but instead of a plus, we write a minus. And so this is cosine squared theta minus sine squared theta. And so that's the identity for the cosine of 2 theta. There's actually 2 more right here, 2 more little identities for cosine of 2 theta. And how do you find these 2 identities? Well, the idea is you can actually plug in for sine squared theta because ooh, why is that square up there, guys? So we need to correct this. I'm not sure why that square wound up right there. It should be right there. All right. And so we can actually solve this for sine squared theta. So notice if you move over cosine squared theta to the other side, what do we get? We're going to get sine squared theta equal to 1 minus cosine squared theta. And so now what we can do is we can take this 1 minus cosine squared theta and plug it into right there. And then what's going to happen is you'll wind up getting 2 of these cosine squared thetas and then minus 1. And then we can do the same thing for the cosine squared theta. So we can solve this for cosine squared theta. And so this would be cosine squared theta is equal to 1 minus a sine squared theta. And we'll take that and we'll plug it in right there. And so what will that give us? That'll give us 1 minus, and we have a minus sine squared theta and another minus sine squared theta, so minus 2 sine squared theta. And we call these the double angle formulas. Or I guess we call them identities. I've put formulas. These are fine. We can call them identities. All right, so let's call them identities here. And then finally, we will be using these power reducing identities here. And so what the power reducing identities do, they reduce powers of trigonometric functions. In particular, we want to look at how do we reduce cosine squared theta and sine squared theta. And these are actually pretty easy to remember. And so what are they? Well, the cosine squared of theta is equal to 1 plus cosine of 2 theta, and then divided by 2. Whereas the sine squared theta is basically the same thing, but instead of a plus, you put a minus. So 1 minus cosine of 2 theta divided by 2. And so those are the identities you're expected to be familiar with. So make sure you know those. If you don't, make a little note card front and back so you know those identities on site. So there's like the basic identities. There are actually lots of trigonometric identities, but these are the ones that we build most of them out of. So how can we use these identities to solve what are called trigonometric integrals? So let's come down here. And our question is, how do we integrate something like this? How do we integrate something like the secant theta over tan squared d theta? And we use theta, right? So we use the Greek letter theta here. Although you could use just x, that would be fine too instead of theta. But when we're doing trig integrals, you'll see we're actually going to use these later in trig substitution. And when we do trig substitution, we use theta. So right now I convert it to theta, but sometimes we also do them with just x. So the idea behind this is just to rewrite secant theta and this tan theta in terms of sine and cosine. And if you do that, these problems, or this type of problem, usually falls out. And so real quick, before we do that, what are trigonometric integrals? Basically, they're just integrals involving just trigonometric functions, right? So for example, you know, this one right here just has trigonometric functions. If you want an example of one that you might not call a trig integral, you could write theta sine of theta d theta. Now it does have one trig function, but because it has this theta in it, you may say it's not a trig integral, it's something else. In fact, in order to integrate this, right, you have to use integration by parts. So integration by parts. And we'll start talking about these techniques of integration and how to decide when to apply which technique, because that is a problem in its self, basically. All right, so to solve these trig integrals, so how do you do it? You basically just use a trig identity. So let's take a look at some indefinite integrals and see how this works. And so let's start here with A. And so I have the integral of secant theta divided by tan squared theta d theta. Now notice, it's not an integration by substitution because I don't see a function and its derivative running around. I don't think it's probably integration by parts. I mean, it could be, maybe you can break it up somehow to make it, to be able to integrate it, but I don't see it. It's not real obvious to me. But it is an integral just involving trigonometric functions and nothing linear, quadratic, or anything else. So that's how I know it's a trig integral. And the trick to this is just to convert these to sines and cosines. So we're going to convert secant theta to a cosine, and we'll do this tan squared theta in terms of sines and cosines. So we'll go nice and slow here. This is equal to the integral, and I write this as 1 over cosine of theta, and then divided by And then tan of theta is a sine of theta over cosine of theta. And that's quantity squared because you're squaring the tan function. And then d theta. So that would be my first step. And notice I have those identities memorized, so it's easy to do. I just plug in. And now here, since I'm dividing by a fraction, I'm going to multiply by the reciprocal. So this is going to be equal to the integral of 1 over cosine theta. And then this cosine theta is now going to move to the top. So I'm going to have cosine, I'm going to square it. So cosine squared theta divided by sine squared theta. And then I have a d theta on the end. So I just multiplied by the reciprocal because that's what you do when you divide by a fraction. I squared it out. And then notice what's going to happen. One of these cosine thetas is going to cancel with one of those. And so this is going to be equal to the integral. I'll have a cosine theta on top. So I have 1 left over on top. And then on the bottom, I have a sine squared theta. And then a d theta on the end. And now when I look at that, I see a function and its derivative. So now I'm going to use integration by substitution. So now there's a combining techniques of integration. And so now I'm going to let my u be equal to sine of theta. And then my du, so I take the derivative of sine of theta and I get cosine of theta, d theta. And I can see my pieces here, how you plug in. I'm going to clean it up a little bit for you guys so you can see it. So this is 1 over, and I'll write this as sine of theta, quantity squared. So instead of putting a square in the middle, I'll put it on the outside, so it's really easy to see. And then times cosine of theta d theta. And so now it's just like a little note card. I'm going to turn over the sine of theta, and I'm going to put a u. So that's going to be equal to the integral of 1 over u squared. And then I have this cosine of theta d theta left over, but that's just my du. So I turn over that note card, and I have a du left. And so if you ask me that question, where'd the d theta go? I say, it didn't go anywhere. It's right behind the du. Or if you ask me, where did the sine theta go? It didn't go anywhere. It's right behind that u right there. You just turn over, it's on the other side. But this is one of my types. So let's make it really clear that it's one of my types. So this is the integral of u to the negative 2 du. It's just a power of u. And so I'm going to add 1 to it. And I'll go slow here. So negative 2 plus 1 divided by negative 2 plus 1, and then plus c. And so that's just equal to, well, negative 2 plus 1 is a negative 1, so it's u to the negative 1 divided by negative 1 plus c, which is really equal to a negative 1 over u plus c. And now I can substitute back in because I made a substitution. I want this back in x's, right? So you make it all about u, and now you bring it back to your x's. And so it's negative 1 over. So you turn that little note card over. On the other side, remember, you have a sine of theta. So you substitute back in. You have sine of theta plus c. If you want, you could leave that as your answer. That's fine with me. Or if you see that this is actually, you can use another trigonometric identity, that's actually a cosecant of theta, you could write this as equal to negative cosecant theta plus c. That's okay too. So this is a standard sort of trig integral. So we use these sort of basic identities to convert it into an integral, then we can do. And this is a great example because we use actually 2 techniques of integration here. A trig integral technique by doing the conversions with the identity, and then we do that substitution. All right, let's do another one. So let's come back here and let's do this part B. And so let's look at this one right here. So part B, so let me just copy this down over here. So B, I have the integral of sine cubed theta cosine squared theta d theta. Now, this is a trig integral because it only involves trigonometric functions. And I have to ask myself, how am I going to integrate it? And I can't do what I did before. Before, I converted to sines and cosines and everything fell out. This one, everything is already sines and cosines. So what do? So let's just kind of go back to these trig identities right here. So you can kind of see what's happening, right? So we can't use this and we can't use this. And so the question becomes, can we use a Pythagorean identity? Mainly, can we use this identity cosine squared theta plus sine squared theta equals 1 to simplify this somehow, or get it into, one of our basic types of integral. So let's take a look at it because you can. All right, so, and how are we going to do this? And so let me write this above here. I'll write the identity above. So we have what? We have cosine squared theta plus sine squared theta is equal to 1. And maybe I should have said first, I don't see a function in its derivative just plainly, right? I do see a sine theta and I do see cosine theta, but one's cubed and one's squared. So if you try to make a substitution, you're not going to be able to do too much. So what do? So the idea is I can either replace this cosine squared theta with stuff just involving sine squared because I can solve for it, or I can pull apart this sine cubed theta and write it as sine squared theta sine theta and plug in for it. And that'll put it in cosine stuff and leave over 1 sine of theta. So that's the idea. If I could pull this apart, right, you can rewrite this as sine squared theta times sine of theta. Notice if you plug in for that sine of theta here, sine squared theta, right, using this identity, so you solve this for sine squared theta, notice everything will be in terms of cosine space, so then you have 1 sine left over. So then you'll have a function, cosine theta basically, and then its derivative, 1 sine theta left over. So let's do this so you can see what I'm talking about here. So I'm going to rewrite this as the integral. I'm going to write sine cubed theta as sine squared theta times sine theta, and then I have a cosine squared theta d theta. And the idea is we want to plug in for this sine squared theta. So up here, I use that Pythagorean identity. I solve for sine squared theta, so it's 1 minus cosine squared theta. And I'm going to plug it in. So I'm going to take this. I'm going to plug it in right there. So it's like another substitution, but it's not integration by substitution. It's just a substitution. Turn the note card over, and there it is. So this will be equal to the integral, and in parentheses, we write 1 minus cosine squared theta, and then times the sine theta, and then what's left over here, sine theta, cosine squared theta, d theta. And then I'll multiply through so you can kind of see what's going to happen. And there's all kinds of ways to kind of solve it from here, but I'm just going to multiply through here, and there. And so what am I going to get? This is going to be the integral. And so when you write 1 times this, you just get this back. So I'm going to write this as cosine squared theta times sine theta. And then minus cosine squared theta times the sine theta cosine squared theta. What do you get? Cosine to the 4th theta times sine theta d theta. So I just multiplied that out, but hopefully you can see now I have a function cosine theta and its derivative sine theta, a function cosine theta and its derivative sine theta. So now if I want to, I could use substitution to solve this, or if you like, I could just integrate it directly because I see a function and its derivative, so I can kind of guess and check. So what I tell you guys is there does come a point when you're combining techniques of integration that if you can see how to do it without using that other technique, you can do that, right? If the problem says, solve the trig integral, I basically solved the trig integral in the sense of using the trick, using an identity. Now, if I want to use substitution, I can, but if I don't have to. So if I wanted to, what I could do here is I could write this as basically cosine cubed theta divided by 3. And then minus, I'll write this as cosine to the 5th theta divided by 5. And then plus c. So that's my guess. Now to check it, how do you check it? You take the derivative. So the 3 comes down, cancels the 3 on the bottom. And maybe I'll do that below here. So let me show you how I would check it. So the 3 comes down. I get cosine squared theta. And that's divided by 3 down there. And then times derivative of the inside, which is a negative sine theta. Oh, so I'm off just a little bit. So notice there's no negative up here. So what do I have to do? I have to add an extra negative here. So if you put a negative there, these become positive, and I got what's above here, right? The 3's cancel, and I have a cosine squared theta sine theta. And same thing here. The 5 will come down, and I'll get cosine to the 4th theta, and that's all divided by 5, so that's where the 5's cancel. And then times a negative sine theta. But I don't have a negative sine theta here, so how do I make that not negative? I put a plus right there. And now that minus and that minus line up. So now I'm good to go. And so there's my guess, and I checked it, corrected for the signs, and I get my answer. And so if you feel comfortable with that, you can do that. If you don't feel comfortable with that, that's okay. You can still do a u substitution. So we'll let u be equal to, and it's cosine theta, and then du is equal to the derivative, which is a negative sine theta d theta. And I'll take care of that negative by dividing it out. So, or if you like, multiplying both sides by -1. So I'll write negative du is just equal to sine theta d theta. And what I can do now is I can just go and kind of plug back in. So this is going to be equal to, and what I have here is a u squared. And I'm going to keep that sine theta on the outside. So in some sense, what I'm kind of doing here is I'm going to erase this. I'm kind of just skipping this step and writing that sine theta on the outside. And then minus, this will be then u to the fourth. And then you have what's left over on the outside. This is your du, and it's a negative du. And so I have this times negative du. And so down here, let's pick this up so you can see what I'm doing. I'm going to draw an arrow down here. So that's equal to, and so that's going to be negative, the integral of negative u squared plus u to the fourth du. And I can integrate that. That's going to be equal to negative u cubed over 3, and then plus u to the fifth over 5, all plus c. And then finally, I can plug back in for my u, so that's cosine of theta. And so I get negative cosine cube theta divided by 3 plus cosine to the fifth theta divided by 5, and then all plus c. All right, so you can see I get back the same thing I got before. So if you feel more comfortable doing u substitution, that's great, do it. But if you're combining techniques of integration, you don't have to, right? Now, if the problem says use substitution to solve this problem, then you have to use substitution. But if it doesn't say that, if it says, just solve the integral, you can solve it. If it's trig integral, you can solve it with an identity. And then you can guess and check to get around the substitution if you want to, right? But you don't have to. All right, let's do one more of these. So we just kind of hit it home. So this is C. And so I'm going to write this down here. So for C, what do we have? So we have the integral of tan cube theta d theta. So let me check that, make sure I got the right one. Yeah. All right. So now, how are we going to solve this trig integral? And it is a trig integral because it's just an integral involving trigonometric functions. And notice, I don't see an obvious substitution to make because I don't see a function and its derivative. You might be able to pull this apart and do it by parts somehow. Parts is a pretty powerful technique. There are some clever ways to do integrals, but it's not real obvious to me. So what am I going to do? I'm going to do this little trig integral, and I have to use an identity. So what identity do I use? So I have to look for or think of an identity that involves tans of thetas. And what pops to my mind is I could rewrite this as tan squared theta times tan of theta. And I have an identity for tan squared of theta, one of those Pythagorean identities. So I know that 1 plus tan squared theta is actually equal to a secant squared theta. So what I could do is I could solve this for tan squared of theta. So let's do that. So tan squared of theta would just be equal to, you have secant squared theta on the right, so secant squared theta, and you should just subtract 1 from both sides. And so what I can do now is take this right here and plug it in from my tan squared of theta. And what will that do? Well, that'll introduce secants and tans together. And we all know that derivatives of tans and secants are secant and tan stuff. So we may have a chance then to solve this type of problem. So let's plug it in and see what happens. So integral. And so for tan squared theta, we plug in secant squared theta minus 1. Put that in parentheses, and we multiply it all by that tan theta on the end, d theta. And so now I'm going to multiply through, and when I multiply through, we'll start seeing some functions and their derivatives. So this is going to be equal to, so what happens when we multiply through here by the tan of theta? We'll put a tan of theta there and a tan of theta there. So this will be the integral, and I'll write the tan theta secant squared theta like this. You could write it the other way also, it doesn't matter. And then minus a tan theta d theta. And when I look at that, my brain kind of pops, right? It dings. It says, hey, I see a function and its derivative. And so what I can do now is I can actually separate this integral because it looks like I can integrate the first part. So I'll separate this. I'll write this as the integral of tan theta, secant squared theta d theta, and then minus the integral of tan theta d theta. So now my one integral becomes two integrals, and one of them I feel like I can do, right? I can do this one because, again, I see a function, and then there's this derivative. So that's just a u substitution. In fact, I could just guess and check on this one if you want me to. I could just say, hey, that's tan squared theta divided by 2. That would be my guess. And the reason that's my guess is when you take a derivative of that, what happens? The 2 is going to come down, and so you get 2 tan of theta, and that's still divided by 2. And so the 2's are going to cancel. And then times derivative of the inside, so derivative of tan theta secant squared theta. So that matches up. So my guess was correct. So if you want to guess, you can just guess and get the answer. Or you could make a u substitution here, let u be equal to tan theta. And then its derivative du, derivative of tan theta is secant squared theta d theta. And then you can just substitute in for that. And so there'll be your u right there. And this will be your du. Right? So that'll be your u and that'll be your du. And so you get u squared over 2. And then you plug back in and you get exactly this. Now, the problem, though, is actually this integral here. So this is another trig integral. And again, I'm looking at this, and I don't see an obvious way to integrate. It's not one of my types. So what do? Well, I can convert this to sines and cosines, basically. In fact, you could have converted this up here if you wanted to sines and cosines and kind of struggle with it if you want up there. That's a legitimate technique, although it's a little bit harder. It makes it a little bit easier if you just use this one identity. And so I'm going to convert that to sines and cosines. So I'm going to write that as sine of theta over cosine of theta, and I have d theta. And now I see it. I see a function and its derivative. So down here, I see the function, and up here is its derivative. So this one, let's do a u substitution on it. So I'll let u be equal to cosine theta, and then du would be equal to negative sine theta d theta. So we take a derivative cosine, right? And so then I know negative du is just equal to this sine theta d theta business. Oops. Sine theta d theta. And so I can substitute in here. So this is going to be equal to, I have, don't forget my tan squared theta that I already guessed and checked on. So tan squared theta divided by 2. And then minus, I have an integral. And then this is my u. So I'm going to write that as 1 over u. And then this stuff right here is my negative du. So negative du. So I make my substitution. And then I can rewrite this. So I'll just clean it up a little bit. So I copy down tan squared theta divided by 2. And then a minus and negative is a plus. And this is one of my types, integral of 1 over u du. And so that's going to be equal to tan squared theta over 2. And then plus ln absolute value of u plus c. And then for that absolute value of u, I'll replace the u with what it's equal to over here. So this is this u substitution. So cosine of theta. So I get tan squared theta divided by 2. And then plus ln absolute value of cosine of theta. And then all plus c. And there's my answer. So that's a good one to kind of see how you can sometimes combine, again, techniques of integration. You can guess and check now that you've applied the original technique, which was a trig integral. And so these are some solid problems to practice. And remember, you can bring these problems back. So I always tell you guys, once we solve a problem, don't be afraid to try to solve it again. These are like free throws. It's like shooting free throws one day, shooting free throws the next day. Doesn't matter if you made it the first day. It's how you what happens each time, basically. But the more you practice, the better you get at these things. All right, so what's next? We have 2 more problems to do. I want to do a definite integral problem. So let's start with this. Right, so let's do a definite integral. And so we want to evaluate this definite integral, and then we want to use a graphing calculator to draw a picture of the shaded region being calculated. And so this is a good one. So it says we want to integrate from negative pi over 4 to pi over 3, this cosine squared theta d theta, and see what it is. So it's a trig integral because it's an integral involving a trigonometric functions only. It's not a substitution right now because I don't see a function and its derivative running around. Is it integration by parts? Maybe you could make it integration by parts, actually. Like that's always a possibility, but because it's just a trigonometric functions, I probably would go with the classic, technique of trig integrals. And so how do you find this integral? And so it's going to be equal to, so I'm going to use an identity. So when I see cosine squared theta, again, bells go off, but different bells, okay? So bells go off in the sense of, oh, cosine squared theta plus sine squared theta is equal to 1. But if you try to use that identity, you're not going to get very far. So notice, if you try to use this identity equal to 1, you can certainly solve this for cosine squared theta. But when you go to plug it in, you're just going to get a sine squared theta there. Basically, there's a 1 on it, right? 1 minus sine squared theta. But sine squared theta, integrating that is as awful as trying to integrate cosine squared theta. So it's like they're of the same level. And so that's not going to work. But we have another identity. So we have those power reducing identities, which say what? It says cosine squared theta is the same thing as 1 plus cosine of 2 theta divided by 2. And so I can use that. I can plug this in over here, and that will actually give me something that I can then integrate. So this is going to be equal to the integral of negative pi over 4 and to pi over 3. And we'll just plug it in directly here. So 1 plus cosine of 2 theta divided by 2 d theta. And at first you may think, oh, I don't think I can integrate that. Well, you can if you just simplify it a little bit. So let me show you. I can simplify this. This is going to be equal to, I can actually pull out the 1/2. So it'll make it easier if you pull out the 1/2. So 1/2 of negative pi over 4 to pi over 3. And I can pull out that 1/2 because divided by 2 is on all of this, the whole entire thing. And then I have left over inside here 1 plus cosine of 2 theta d theta. And those are actually close to your types. In fact, 1 is one of your types. So you can integrate a constant. So here we'll put theta. So we don't put x, you put theta because we're integrating respect to theta. And then I'll write plus, and here to integrate cosine of 2 theta, it's just a guess and check, guys. So I'm going to guess sine of 2 theta. And that's going to be evaluated from negative pi over 4 to pi over 3. Oh, and don't forget your 1/2. And so we have a 1/2 kind of lurking out here, 1/2, and in parentheses, all this stuff. And so this was my guess right here. And guess what? My guess is going to be a little bit off. So I got to check it. So what you do is you just take the derivative. So take the derivative of sine of theta. And so that's really cosine of 2 theta, right? So the derivative of sine of 2 theta is cosine of 2 theta times the derivative of the inside times 2. So what are we off by? We're off by a 2. There's no 2 right here. There's just a 1. So how do you take care of the times 2? You just divide this by 2. So you divide it by an extra 2. And now notice, if you divide that by 2 and now take the derivative, you get cosine of 2 theta divided by 2 times 2, and the 2's cancel. And you get your answer. And so then this is going to be equal to, so this is equal to what? This is equal to 1/2 theta plus sine of 2 theta divided by 2 from negative pi over 4 to pi over 3. Now, if you really struggle with that, you could separate these two integrals. You could do the integral of 1 and the integral of cosine of 2 theta, and you could do a u substitution on the cosine of 2 theta. You let u be 2 theta, your du would be 2 d theta, basically, and then you could do that. But I find it's just a little bit easier on these to guess and check. All right, so guess and check. All right, so down here, now we need to evaluate this integral. So nice and easy, there's no rush. So we write 1/2, and we're going to plug in pi over 3. So we're going to get pi over 3. And then plus, I'm going to write this as 1/2. And then sine, and when you plug pi over 3 in for theta, you're going to get 2 pi over 3. In parentheses. And then minus, now we're going to plug in negative pi over 4. So we have 1/2, negative pi over 4, and then plus sine. Oops, I forgot my half there. Let's write that half there. So then another 1/2, and then sine. So when we plug in negative pi over 4 here, you get 2 times negative pi over 4, which is negative pi over 2. And so now let's clean this up a little bit. So what do we have here? Basically, I'm going to multiply through by that half. So I have a pi over 6. And then I have plus a 1/4. So you multiply through by the half here. And I got to figure out what sine of 2 pi over 3 is still. So I'll take a little bit of work. And then minus, and I'll multiply through by a half here. So I have negative pi over 8. So that's going to be a plus pi over 8. And then minus a plus is a minus. And then I have 1/2, or 1/4, I'm sorry, because I multiplied through by a half here. And then sine of negative pi over 2. So now let's figure out what these values are. So it's going to be equal to, I want to figure out what the heck is sine of 2 pi over 3 and what the heck is sine of negative pi over 2. So the way you do this is you got to figure out where these angles live. So all students take calculus. And 2 pi over 3, that lives in this second quadrant right here. It's like 60 and 60. So it's like 120 degrees. So there's 2 pi over 3. And so I now know that this is the same as sine. My reference angle here is pi over 3. So it's just a sine of pi over 3. And it's positive because it's in that second quadrant. The sine's positive. Negative pi over 3. So where does that angle live? Negative pi over 3, or negative pi over 2, I'm sorry, is down here. Right, so here's my angle. It goes down. That's negative pi over 2. And I actually can read that one off because it's on the unit circle. So it's just negative 1. So sine of negative pi over 2 is just negative 1. And then finally, for sine of pi over 3, remember that table kind of lives in my head where I have these angles. 0, pi over 6 is 30 degrees, pi over 4 is 45 degrees, pi over 3 is 60 degrees, and pi over 2 is 90 degrees. And if you want the sine of these angles, these are my angles theta, when you plug in 0, you just have to remember 1. Sine of 0 is 0. This thing gets me nowhere. So it goes root 0, root 1, root 2, root 3, and then root 4, and they're all divided by 2. And so in my head, I just kind of count up, and I see at pi over 3, you get root 3 over 2. And so this is going to be root 3 over 2. And so I'm going to get pi over 6 plus I have 1/4 times root 3 over 2, which is root 3 over 8. I have plus pi over 8. And then I have a minus, and so it's a negative 1 times a 4, so it's going to be plus 1/4. And now I need a common denominator for all of these things to push them together. So what's the common denominator? I think it should be 24, I think, right? So I'm going to multiply this by 4 on top and bottom. So I'm going to have 4 pi plus, I'll multiply this one by 3 on top and bottom. And so I get 3 root 3. And then plus, I'll multiply this by 3 on top and bottom. So 3 pi. And I'll multiply this by 6 on top and bottom. And so then I'll have plus 6, and that's all over 24. I can combine like terms, so 3 pi and 7 pi, or 4 pi and 3 pi are 7 pi. So it's 7 pi, and then plus 3 root 3. And my goodness, plus 6, all divided by 24. Woo! What an answer. All right, hand hurts. All right, so that's a nice one. All right, so that's a good one to practice. It's got a lot of good stuff in it. Of course, there's always a chance that I made a silly mistake somewhere. So in order to check my work, I'm going to take out my calculator here, and I'm going to graph the original function. So if you remember, the original function was a cosine squared of x. So to put that on my calculator, I write cosine of theta. So I put x though instead of theta. And then I square this thing. So I square it. And I put the whole thing in parentheses, notice. And so there's cosine squared, and I make my window, and my window, I want to go from negative pi over 4 up to pi over 3, so second pi over 3. And sometimes this window will work, and sometimes it won't. It depends on the rounding, but so we'll try it, and we'll fix it if we need to. And so then I go down to zoom fit to get a nice looking graph. It'll fit the output to the input that I put in there. And so there's my graph. And then the question becomes, how do you find the area there? So how do you find the integral? And so down here, I hit number 7, and I'm going to do negative pi over 4. And then up to pi over 3. That's my upper limit. And I'll hit enter. And if it says error, what that means is my windows, they're rounding on different screens. So I'm going to go back to my window here, look at the number, negative 0.7, and make that a little bit smaller, so like negative 1. And up here, it's 1.04, blah, blah, blah. So I'll make that a little bit bigger. Let's just make it 2. If you want, we can just go right back to the graph. You don't have to resume fit it if you don't want to. And then now I'll do the same thing I just did. Go down to number 7 and type in negative pi over 4. And type in pi over 3. And now it's going to work. And it shades in that region, returns this number 1.38, blah, blah, blah. All right, so let's graph this basically. So we're graphing here from negative pi over 4 to pi over 3. It basically just goes up and kind of comes down. And what did it look like when we shaded in that region? You'll be able to do a much better job than I do here. And so then you get this little piece here and shade in that region there. And what I'm interested in is that number. So that number is 1.38, 1.3828 ... And the question is this number that number? So let's take a look here and see. So quit here and we plug it in. So 7, I got parentheses around this. So it's left parentheses 7 pi. I feel like we're going to be off a little bit. I feel like it's too big, but we'll see. And then square root of 3 and then plus 6. In parentheses, divide by 24, hit enter. Oh my goodness. Right, we got it. Right, so it's perfect. I thought it was going to be too big, but it's not. Right, it's right on the money, guys. Right, so there it is. Right, again, it's a great problem to practice. It's got a lot of great stuff in it. Okay, I have one last problem. This will go real fast, so don't worry. This last problem is just a little bit of a trick. So there's one function that I only really know one way to integrate it, and that's a secant of theta. All right, and a secant of theta uses a trick. So once you see the trick, hopefully it's like, oh, I'll remember that, because I did when I saw. I was like, oh, okay, that's tricky. So how do you integrate a secant of theta? Now you can convert it to sines and cosines, but it really won't help you. So the easiest way to integrate this is just to remember this trick. So the way you integrate secant of theta is you multiply on top and bottom by the same thing, but it's a little bit weird. I multiply by secant theta plus tan theta on top and bottom. And you may think, well, that's weird, but in a minute, it'll become clear why you do this. Now, notice you can do this because this is just the number 1, right? Secant theta plus tan theta divided by secant theta plus tan theta is really just the number 1. But when you multiply through, check out what happens. So on top, we're going to multiply through by this secant theta. So you're going to get secant squared theta plus a secant theta tan theta on top. And then on the bottom, you have secant theta plus tan theta. And this is all d theta. And if you think about this a little bit, you'll realize that, hey, here's a function on the bottom. What's the derivative of that function? So what's the derivative of secant theta? Well, the derivative of secant theta is just secant theta tan theta. And then you have plus, what's the derivative of tan theta? And that's secant squared theta. And that's exactly what's written on top. So you have the derivative you have the function on the bottom and the derivative on top. So there's a function and its derivative. So this thing, if you want, we could rewrite as 1 over secant theta plus tan theta. And then we can move that secant squared theta plus secant theta tan theta. So secant theta tan theta. And then all d theta over here, we should probably put this in parentheses to make sure it's correct. And again, I see the function right here. And then there's its derivative. So if you want, we could do a u substitution to integrate this, or you could skip it and just guess in and check. But we'll do a u substitution. So I'm going to let my u be equal to the bottom, secant theta plus tan theta. And then we already know what our du is because you just take the derivative, which we did right here. And so you get secant theta tan theta, and then plus the derivative tan theta is secant squared theta. And then we have d theta on the outside over here. I'll put little parentheses here. And so now we make our substitution. So it's the integral of 1 over, and this is our u right here. So we replace that with u. And then this whole thing right here is just our du. And this is one of our types. So it's equal to the ln of absolute value of u plus c, which is equal to, now we replace u with what it's equal to. That's secant theta plus tan theta. So ln of absolute value of secant theta plus tan theta. And then plus c. And that's the answer. So this one comes by a trick, right? And the trick, let's see if I can scroll out a little bit here. The trick is just to use basically an identity, 1. But that 1 is found by using secant theta plus tan theta. And again, this is the only way I know how to integrate secant theta in an easy sort of way. And so once you see it, it's not so bad. And remember, I actually could probably integrate it right here. And if I see a function on the bottom, its derivative, I know it's going to be ln of absolute value of secant theta plus tan theta plus c. And the reason I know that is because if I take a derivative of this thing, the derivative of ln is 1 over. So you write 1 over secant theta plus tan theta. And then we multiply by the derivative of the inside. And that derivative of the inside is exactly what we have on top. So secant theta tan theta plus a secant squared theta. So you see, like, you can kind of just guess and check if you want to, as long as you know the trick right here. Okay, guys, that's all I got for you today. See you in class tomorrow. Have a good day.